Good day, and welcome to the 2019 Jump into STEM webinar series. Jump into STEM is sponsored by the U.S. DOE's Office of Energy Efficiency and Renewable Energies Building Technology Office, with support from Oak Ridge National Laboratory and the National Renewable Energy Laboratory. With Jump into STEM, our goals are to emphasize cultivating diversity of thought by underscoring the importance of interdisciplinary teams inclusive of women and minorities. The Jump into STEM program works with university and college professors from a variety of disciplines to support creative building science challenges that can be integrated with coursework curricula. Jump into STEM's network includes leveraging public-private partnerships with industry partners and STEM organizations to support the annual student challenges and events. With this slide, you can see a quick snapshot of how the Jump into STEM student competition works. Eligible students can compete for up to 4 paid internships at either Oak Ridge National Lab or the Renewable Energy Laboratory. You can go to jump.ideascale.com to view the eligibility requirements and the full schedule. When there, click on How It Works at the top of the home page to view a step-by-step process on the eligibility, building a team, ideation, and idea submission requirements. Also on the top navigation bar is the schedule for the Jump into STEM 2019-2020 competitions. Eligible students can participate in any of the 3 concurrent online challenges that are running right now through November 15th. These challenges are supported by an online webinar series designed to provide insights on industry practices, market issues, and other supporting resources to help student teams build and generate their idea solutions. Additionally, throughout the competition, Jump into STEM will host periodic Jump-a-thon events to spur innovation and creative thinking. After the 3 challenges close on November 15th, the Jump into STEM team will run a judging process to select finalists who will compete on January 31st, 2020 in a final event competition hosted at the National Renewable Energy Laboratory in Golden, Colorado. During this final event competition, judges will award the 2020 Jump into STEM internship winners. Again, please visit jump.ideascale.com for details on how it works, eligibility requirements, and the schedule updates. The first Jump into STEM challenge topic is focused on smart sensors and controls for residential buildings. Participating competitors interested in this challenge topic should develop a unique application that uses sensor data in residential buildings for the purposes of reducing energy, maintaining or improving occupant comfort, and/or to provide better responsiveness to the electric grid. Strong Ideas will present the proposed approach. They will identify sensor data and how the data will be used. The idea should also discuss the anticipated impact and a tech-to-market plan for this application. The second Jump into STEM challenge topic is to design a healthier and energy-efficient air distribution system for the small commercial building setting using your local climate zone. Strong Ideas will identify a novel system for the selected climate zone and will present implementation of the solution in a hypothetical or existing building. Solutions should articulate the expected impacts from the design system and also include a tech-to-market plan. The third Jump into STEM challenge topic is focused on pushing the envelope with innovative wall retrofit designs. Students are challenged to design a residential wall retrofit product or system that can address replacement or supplement of current leaky and unhealthy walls. Strong Ideas will identify how the wall retrofit will work and will be inclusive of details on how to address the issues of moisture and air tightness. Additionally, Idea Solutions should address one or more of the following issues: low indoor air quality, high energy costs, and/or high retrofit costs. Like other Jump into STEM challenge topics, this idea solution should include a tech-to-market plan. So if you have questions, please visit jump.ideascale.com, or you can email jump@ornl.gov. Now, up next are the webinar series supporting the 2019 to 2020 Jump into STEM challenges. Third in the series is a presentation on field experiences in implementing wall retrofit solutions, co-presented by Matt Waring from Virdiant along with Bill Riggs. Originally from Richmond, Virginia, Matt is the son of a single-family contractor and grew up around construction and on-job sites. He has worked as both a single-family and a multifamily superintendent. With 5+ years with Virdiant, Matt has worked as a technical advisor, project manager within Virdiant's multifamily team, and he is now serving as the technical director working with Virdiant's in-house field personnel and project management staff to provide rating and construction consultation services to a range of clients throughout Virginia. Bill Riggs was born in Richmond, Virginia, and attended the school at the University of Vermont in Burlington. While studying environmental sciences, Bill worked for a small independent contractor that performed energy audits and weatherization work. Upon coming back to Richmond, he worked for a single-family contractor that specialized in deep energy retrofits. Bill is currently serving as a technical advisor with Virdiant, providing verification of various green building programs as well as consultation services. So please welcome Matt and Bill Riggs.
All right, thank you so much, Caroline. My name is Matt Waring. Caroline did a great job introducing us. Thank you so much. We're really pleased to be a part of this Jump into STEM program and this challenge specifically. I think that there's a lot of opportunity out there, and I think that's a good way to look at it. It's a challenge, but it is there's a lot of opportunity for improvement. So I'm hoping that we can give you a little context on that moving forward here, and also kind of show you what we deal with day to day in the field trying to address these types of issues. So yeah, let's hit that next slide, please, Caroline. So quick background about Virdiant. We are a local 501c3 nonprofit local here in Richmond, Virginia. Our flagship program is the Earthcraft Green Building Program. It's a points-based green building program, much like LEED or your other green building programs. We are specific to the Southeast. We work on multifamily, single-family, light commercial, and we also have a communities program. So we have a range of programs under that Earthcraft banner that we institute. We primarily work here in Virginia. To date, we have certified upwards of 23,000-ish dwelling units across the state of Virginia, a little bit in Maryland, and in the DC area as well. So that's a little bit about our organization. We've been in Richmond since 2006. So next slide, please. So here's Bill and myself, so you can get a visual on us. Bill standing there in front of the flux capacitor, about to do a little time traveling. No, that's our blower door. That's a light commercial enclosure test that we were doing up in Northern Virginia, and then I'm just boring in front of a tree. But we're your presenters today, and we hope to give you a little background here and some additional information on the building science behind what we're trying to do. Next slide, please. Thank you. So today, just a quick overview of what we're going to be going over. I'm going to give you some context about climate zone, kind of where we are in the construction industry with regard to this issue and the challenge in front of you, and overall just kind of construction as well as physics and buildings, and then design decisions and real-world strategies about how this is actually accomplished in the field currently, which I think you'll find to be interesting, but also not ideal, which means, again, ripe with opportunity here. Next slide. So some historical context. I'm actually a history major, and so this jumps out at me always. I'm not using that major now, but I'm heavily interested in building science, and I always think this is a very interesting slide. So you can kind of see overall energy use split there in around the 1960s. and residential buildings end up becoming quite a bit more, residential and just buildings in general, become quite a bit more energy use intensive. And so the real reason for that is space conditioning, and the introduction of space conditioning into buildings around that time period, and it becoming more commonplace in the residential industry. So as we start using energy to condition the spaces that we inhabit, our energy use kind of goes off the charts, whereas some of these other sectors have really stayed pretty level over that time period. And so this is not a super up-to-date slide, but I think that you can get the historical context of why this is such a big issue and how much energy we really are using in these homes. So yeah, next slide, please. And so to kind of build on that, Caroline mentioned briefly that, many of these 1975 homes and before were built to little or no energy code. I think looking at this, I pulled this directly off of energycodes.gov. This is as of December 2018. So you can see how many states are still behind on overall energy code, as well as how many states really do not actually adhere directly to an internationally recognized code. So, if you can see this in 2018 or 2019 and say, wow, it's kind of, a hodgepodge of code out there. Well, think about what it was in 1975, and how much it really was more or less the Wild West. You could get away with kind of murder with regard to overall buildings and what went into them. There were kit homes at that time, people building their own houses. So there are a lot of variables out there in construction type, but I think again, this really highlights the opportunity across the nation to improve upon existing buildings. And I think Bill and I both are in agreement that renovation is kind of the greenest form of construction, in that all of the resources are pretty much right there in front of you. It's not cultivating new resources in order to kind of maintain or retrofit a single family home that's existing.
For sure.
Next slide, please. So I think in the challenge, it kind of outlines where, that you should be, or ideally you are going at this from a climate zone with which you are familiar. So where your university is located, I think is how it's worded in the challenge. This is just a good kind of visual view of where the climate zones kind of fall within the country. We are right there under that star here in Richmond, Virginia. We like to think of it as one of the more difficult places to build. We get a little bit of Maine and a little bit of Florida throughout the year, just kind of depends. But we build differently in different climate zones. So, addressing this issue from a different climate zone, say from Maine, would be different than how someone in Florida would address the same problem. So I think that's important to note. One thing I'll just add to that is that, here in Virginia, if you're on the Eastern Shore, you're in one very distinct climate zone. And if you're in the tip of Virginia out west, you could almost be in climate zone 5 there. And really, some of these lines are a bit arbitrary. So, the flexibility of being able to use a product or, retrofit a home with a product across many different climate zones and many different building conditions is very important to us and what we do, even just in the state of Virginia. So I think that's important to kind of take into account and understand that that is something that, you're watching HGTV. We're not putting plastic in our walls here, but you might be doing that in Maine, putting a vapor barrier, a class 1 vapor retarder in a wall system. So these are all things that, would have to be addressed in a retrofit scenario. Next slide, please. So quickly, I wanted to highlight, and then you can hit the next slide. This is just the table from the 2015 IECC R value requirement. So you can see there in the red box highlighted is the R value per climate zone. So again, highlighting the fact that by climate zone, the R value requirements from a code perspective are different. And that makes sense. I mean, you're going to want more insulation, thermal protection in Maine than you would maybe in the middle of the country here in Virginia, just based on the range of temperature that you see. So obviously, again, you can see there the wood frame R value for an upcoming building here in the state of Virginia is R20 or R13 plus 5. That plus 5, where you see that, is a continuous insulation value. So an external to the wall system insulation value is something that would go behind a cladding. not in the cavity of the wall system. So that's how you read that. And that's all readily available. I think that we have some links here. We'll include that and get them to Caroline so she can include those links too on the website moving forward. Next slide, please. So having talked about sort of climate zone and taking that into account when you all are addressing this issue, we wanted to kind of talk to you about the history, the climate zone, and then what we do when we look at a home or look at a set of drawings and we move this problem out of the theoretical and kind of into the field, into the real world. And so, while you're thinking about the design of a wall and what it should do, essentially a good wall is an environmental separator. We build buildings to get inside from negative 60-degree temperatures like we're experiencing out west right now. So we don't have a lot to complain about. I think it's 40 here today, but at the same time, it would be a lot more difficult to provide this webinar to you all if were we sitting outside. So, the entire intent here is to separate our internal lived-in environment from the external environment. And a good wall should have an air control layer, a moisture control layer, and a thermal control layer. We want to prevent draftiness, wind from blowing directly into the building. We want to prevent rain and bulk water from entering the building. And then we have to have some sort of thermal control, which is the insulation portion of this equation. So these are really the three main things that a wall must do in order for it to function properly. Next slide, please. So traditional energy retrofits typically focus on a crawl or a basement and then an attic. Next slide, please. And that is because these places are accessible. That is a big reason. It's easy to get into an attic and say, hey, I could add some insulation here, whether that's to the roof deck or even to just the ceiling plane. But the same can be said about a crawl and a basement. Now, buildings' roots are really that crawl or basement. And so due to stack effect, much of the air in a building does flow upward and out of the roof assembly or through that ceiling plane. So, both of these are very effective retrofit strategies. But if you look at that simple drawing of a house, if you look at that in terms of a beer cooler, the top and bottom of a beer cooler doesn't do anything in and of itself to keep your beer cold or your sodas cold. You guys are 18. But if you think about it that way, it works the whole house works as a system, and that's the way we approach everything. All of these components work together. And so by completely ignoring the blue square there, we're really missing a lot of opportunity. 4 sides to our 6-sided box, where retrofit is a possibility, even though it may be a more difficult possibility. Next slide, please. So what we kind of talked about before kind of goes hand in hand with the very fundamentals of building science and physics in general. And so when we're talking about building science fundamentals, it really is kind of basic physics, high school level, college level physics, right? It's the movement of heat, moisture, and air. So if you click that next one, the movement of heat in a building is very important, right? We want to keep the interior temperature to about 70 degrees. Caroline, if you don't mind hitting that next slide. So, the same forces for heat movement work in a building as they do in anything else, right? Conduction is heat moving through a solid material. Convective loops are present in all homes, and we'll talk a little bit about that in wall systems. And then radiant heat. The best really example of radiant heat is just the sun warming the earth, right? So these are all things that are happening in the built environment and that we need to control. We're either taking heat out of the interior space or putting it back into it in the winter like we're doing now. Next slide, please. And just as important is the movement of moisture within a space. And so, and maybe more so in some instances, this is the one, moisture and moisture problems in buildings are one of the largest drivers of cost overall in buildings in the country. I think there are staggering stats with regard to building failures, component failures, and building failures in general as they relate to moisture intrusion in buildings. And so 1 is bulk water there, 2 is capillary action, and 3 is infiltration. air infiltration. Air is a moisture transport system, and that's something we're going to talk pretty heavily about here as we keep pushing through there. Bill wants me to talk about number 4 because that is inward solar vapor drive, and that just makes us sound very smart. But when water hits the side of a building and the sun comes out, you have 2 forces, both heat and air, moving inward into the building. So heat and moisture rather. And so heat and air and moisture all move the same way. They all move from areas of high concentration to areas of low concentration. So nature is seeking an equilibrium. And so all of these 3 components need a driving force, basically. One very wet area, and then that wet area wants to move to more dry areas. That's just how water works. The same thing with heat. So, all these kind of fundamentals are important to take into account when you're thinking about overall design decisions with regard to wall retrofits and how the system works as a whole to keep all of these components in or out.
Yeah, and to quote somebody, much more intelligent than myself in this field, there's 3 things that destroy a building, and it's water, water, and water.
Yes.
So those are the things you want to be on the lookout for.
That's exactly right. That's great. Next slide, please. So why moisture is important. This is 7-year-old framing, and this is really torn up because of moisture intrusion into the wall system. And so, mold, mildew, organic growth, these things are very important to health and safety of occupants, right? People in buildings is what we should be designing around first and foremost. But we build buildings out of mold food, organic materials. And every day somebody comes up with a new material that we input into buildings that works for the same purposes. But the majority of our buildings are made out of wood and paper. And these things are mold food. So, as you start to increase the moisture content in a small enclosed space, you will get organic growth, and that growth will just feed on the actual material that you built your building out of. These are the things that we try to avoid every single day so that we don't run into these type of issues. And it really is not in a hot, humid environment like we find ourselves in here down towards the eastern part of the state in Virginia and much of the country. This can be a gigantic problem. If you're in Arizona, this may not be as big of an issue for you. But again, these are the biggest building failure issues that we see, and so we're kind of coming at this from our experience. Next slide, please. So thermal control. So for optimal thermal performance, what are we looking for? What's the goal here, right? Insulation should fill the cavity completely, like your hand fills a glove. Every cavity is a 6-sided box as well. You want insulation to fill the cavity front to back, top to bottom, left to right. And that's what we grade insulation on 1, 2, and 3 levels, a 3 being a pretty poor insulation install. So a grade 1 insulation is free from voids and compression. And should encase any infrastructure. You shouldn't have wires or plumbing, compressing the insulation as it's installed. This creates convective loops in the actual wall system, which degrades the overall R value of the actual insulation. So when I say that, I mean if it's cold on the outside of the building, the air is more dense as it touches that exterior surface. It falls to the bottom of the cavity. As that air works towards the inside, it actually warms back up and creates a loop, and that air rises. And so all the time, air is rising and falling in a wall cavity, which degrades the overall R value of that insulation. So you may be paying for an R19 and you may be getting an R5. So, install quality is a huge issue and something that is definitely more difficult in a retrofit scenario, in many retrofit scenarios. Ideally, an insulation product would have high thermal mass. Great sound attenuation. You want it to be quiet in your house. You don't want to hear every siren and person walking by. And permeability in wall systems for us especially is a very big issue, which we just kind of talked about. But we know these buildings are going to get wet, right? They get wet during the life cycle of the building. They also get wet during construction. So, water is going to get in, but we have to be able to have it dry one way or the other. So these are all very important aspects to kind of take into consideration when we're talking about insulating or re-insulating a building. Next slide, please. Just a quick rundown on how insulation works and like weighted R values. So, we have a bunch of wood in the wall system, and that is R1 per inch. So every 3.5 inches, it's R3.5, and then in between that cavity you get R19. So overall there's a weighted average for the R value of the system, and that's an important thing to remember. So small gaps and voids make it's like you go and you have 5 tests and you get 4 100s and a 0, and somehow your average is a 70, right, in the class, even though you got a bunch of hundreds on tests, right? Well, it's the same thing. Insulation and the overall coverage of insulation works the exact same way. R38 installed in a roof or an attic system with 5% gaps drops that overall R value to a R27. So again, you're paying, your homeowner or your client is paying for R38, and they end up with an R27. So a 30% reduction in what they're actually paying for. So just a quick rundown. R is just resistance to heat and flow. A U value is something that an assembly gets, multiple materials, and that is just the inverse of an R. So 1 divided by the R. And these are just the 2 ways that, like, a window system will get a U value, an insulation product gets an R value. So just things to remember. Yeah, so I think that's the majority of that stuff. So yeah, next slide, please. Yeah, so I'm gonna let Bill take over here for a minute, yeah, I think the important thing to remember here is just one, the historical context is we're ripe for change here, and 2, you will see what we have to do in the field here, what it takes in the field to actually get some of this stuff done, and that's really where the rubber hits the road.
Right. Cool. So you've got a bunch of different insulation types at your disposal here when retrofitting a wall. All of them have different characteristics and can be used in different applications. So foam, comes in a couple different varieties. You've got spray foam, and you've got a rigid board that can be used. The rigid board comes in a bunch of different types. It can be, it's XPS, EPS, and polyiso. Those are all great for exterior applications, whereas spray foam, is great for hard to reach areas, and comes in 2 different varieties. That's open cell and closed cell. So open cell foam, like it sounds, it's more expansive and is often water based. It has a lower R value than its counterpart, closed cell foam. And so closed cell foam, it's very dense. It's great for achieving air tightness and has high R values, but it has a very low perm rating. So that's something to consider. Cellulose is just chopped up recycled newspaper, probably my personal favorite insulation out there, but it's okay to be a little biased. Fiberglass, that can be, that's just like it sounds, little glass fibers that get blown across a mesh screen, and that's how it's made. So that can be blown in or is in a bat as well.
That's probably your most common insulation product that we see on the market still, and comes in blown and that being a little bit more difficult to install properly.
Yeah, if you're unfamiliar, it's that little pink stuff you see in walls all the time. So, and then we've got rock wool, which I believe is a brand name, but it's mineral wool. It's made from slag. That's an interesting product because it comes in a board form as well, and it's hydrophobic, so it actually repels water. And next slide. So, one of the most important things is, a site examination when determining your work scope. This is probably one of the most determining factors. And so walking the exterior of the site can give you a great idea of what this project is really going to need. And so one of the first things to look at is cladding type. If it has siding versus brick, that can really change your scope for your retrofit. You want to look at bulk water. So we're looking at site grade to make sure that you have positive flow away from the foundation. Any sort of negative slope around the foundation is going to really invite that water into the foundation. Looking at gutters and roof overhangs to make sure that water is properly discharged. House orientation can play a big role, and similarly with surrounding vegetation. If you're driving around and you see somebody's roof covered in moss, that's just because they're not getting enough sunlight and there's not enough drying potential on that roof. So all of these things can play a huge part.
Right. And so for your challenge, a lot of this you don't necessarily have to take into account, but in the real world, these are all things that absolutely have to come into your decision tree when you're making these decisions and trying to move forward with a good, healthy design for both the homeowner and the home itself.
All right, next slide. So here we've got a little fancy tool that we like to use in the field. It can be extremely helpful, but it's thermal imaging, and it can be used for a variety of things in the field. But on the picture right here, what you're seeing is a void in the insulation of this home, and so you can actually see the studs in each individual bay running vertically, and then you've got that bright hot spot in the middle that's showing where it's uninsulated.
Right. And you can also, just of note, I think, is the kind of thermal loss around the windows and the fenestration in this picture. It's just always kind of jumps out at me. It's how much loss you get around those window openings. So again, a weighted R value, weighted U value of the overall assembly is important.
Right.
Trying to improve the overall performance of the project.
All right, next slide. Cool. And then along with the exterior site assessment, you got to take, at least we have to take the client goals into account. And so, budget is often probably one of the largest concerns. We want to make sure everybody gets a good return on investment on the work that's done. But then comfort is a serious concern. If someone is, sometimes you get those large discrepancies in temperature between the first and second floor. That can often be remediated by, air sealing and insulating the attic plane. So those are important things to take into account before you decide on a scope. And then intrusiveness, if somebody works from home during the day but wants to improve the performance of their home, but they can't interrupt their work schedule, then that can play into the scope as well. And then lastly, indoor air quality can play on scope if you have anything to.
Yeah, I would just say, goals of the renovation. I don't want to gloss over that too quickly. In that, a lot of what we do is focused around, obviously budget, but homeowners have specific goals. They want to be able to use, that bonus room in their house or that ancillary dwelling unit. They have specific goals, and so it really helps to narrow the scope of what you're trying to do and hone in on what the actual problems are for the homeowner, because client satisfaction on the back end is important for everybody, right? So this is just real world stuff that we deal with day in and day out, and if the homeowner is happy with the house they're living in or is unhappy currently, you can help them be happy. That's an important aspect of what we do. Indoor air quality, I think this challenge really does a good job addressing the moisture concerns and wanting you all to focus on the moisture concerns. This, basically organic growth in buildings is a huge concern from a health and safety standpoint for homeowners. So again, we just can't hit that enough.
And next slide. So here we've got our first real world example. This is probably, the highest cost strategy that we'll be showing you. This one, the homeowner desires the ability to keep as much of the existing house as possible. It is a pretty intrusive strategy. So, what ended up being done is that the cladding and the sheathing along the exterior was completely removed. And what he's doing, he's spraying closed cell foam into the wall right now. So that's, you're getting a nice air tightness from the closed cell foam. And that's actually going to be paired with some fiberglass insulation available on the next slide. So I guess, and I'll talk into the next one as well. So this section of the home was then re-sheathed with cis sheathing, which is a structural insulated sheathing. This combines the insulation with the sheathing, reducing labor costs, and which is often more used on new construction. But see, from behind, we've got the closed cell foam in the wall. We've got the unfaced fiberglass bats on top of that. It's kind of a tried and true method in the field, just called the flash and bat. And it's a great combination between the products because it relies on the air sealing of the spray foam, which then improves the thermal performance of the fiberglass bats.
Right. Yeah, Bill, they added a layer of, so in place of OSB, they used structurally insulated sheathing on the exterior to prevent the thermal bridging. So we saw some thermal bridging in that thermal camera image. and that's what we refer to when you're talking about the low R value of a piece of framing member, like a wood stud. So they reduced that, as well as included all of this insulation into these cavities, which was not there prior to. And how did this thing end up on the back end, Bill, performance-wise? It was near zero, wasn't it?
Yeah. So yeah, we like to call it a near zero energy remodel. But it was tied with new HVAC system and solar PV on the roof, which reduced the electric bills to about just an $8 service charge per month for the year.
So, right. So obviously something that works very well, but this was a full-on, more or less, gut rehab.
Yes.
What drove you to this strategy, I believe, was the desire for the homeowner to maintain as much of the existing structure as possible too.
Right.
She wasn't living in the space, but she didn't want to throw a bunch of plaster in the trash if we didn't need to.
Yep.
Right. Cool.
All right. Next slide. So here we've kind of got mid-cost, low intrusiveness on retrofit opportunities here. And kind of one thing that drove us to this is that, the cladding needed to be removed anyway. You can see the old cladding on the side, and which provided a good opportunity to wrap the entire building in exterior continuous insulation. And so, one thing we hear a lot in the field is that, it's strange that we stuff insulation into stud cavities and rely on that completely. You don't stuff a sweater between your ribs when you're cold. You put on a jacket so that you're completely encased in insulation. And so really the industry needs to move towards more continuous insulation across the board. So, and just kind of covering some of the, this photo was taken partially through the renovation. So there's a little gap in the insulation there pictured right. You just want to make sure that your insulation is as continuous as possible, and all these seams in the insulation should be taped as well.
Right. And then just like to kind of hit on the point of, new material meeting old material and depth issues with regard to adding continuous exterior insulation. I mean, all of these, from an architectural standpoint, all of these materials need to be able to be married up to one another and show as a kind of contiguous exterior cladding system on the back end that is aesthetically pleasing. So you can't just bump out 3 inches of foam and not have some way to address that transition back to other cladding if you're not doing this to all 6 sides of the building or what have you. So, again, design decisions, it's all got to be taken into account. The whole thing works as a system.
All right, next slide. So here we've got, this was some exterior insulation that was done along the roof line. The reason for doing this was that the homeowner wanted to kind of maintain the aesthetic from the inside as much as possible. So
had an exposed beam,
yeah.
Cathedral ceiling on the interior, and they didn't want to go and stuff a bunch of insulation into a very pretty interior ceiling, but they did want to move the dew point to the exterior.
Right.
So that's something we could probably hit on here on the back end too.
Yeah, so we ended up removing the entire roof, re-roofing the entire thing. So it's covered with 4 inches of polyiso cyanurate, which is one of those rigid foam insulations that I mentioned previously. And it provides a great example of, a good installation for exterior foam. You want to make sure that all those seams are staggered and properly taped.
Both horizontal and vertical seams are all staggered. 2 layers. They have all of their underlayment already laid down there, and then the actual roofing goes back over top of that on the back end.
All right, next slide. So this is kind of one of the most tried and true methods for retrofitting an existing wall. This one, we're doing it from the exterior because, like I mentioned earlier in the slide, the homeowner actually, she worked from home and so didn't want any sort of intrusive work scope. So we're lifting up existing aluminum siding, drilling through the sheathing from the outside, and then filling it with cellulose insulation. And this is a, fairly low cost solution and can be pretty easy to do, especially, that we're doing this in Vermont winter. So it's not
Yeah, it just is going to depend on your cladding type too. I mean, most lap sidings you can get this much play in. This is aluminum, so some your hardies you're not going to be able to really pry up, but so hard on a hardy plank, so
Right.
or like a cementitious kind of cladding. So it all plays into the building type, and they were able to do this, and they executed on it well. But that's not always the case. Brick, if you have a brick home, there's no way that you can do something like this.
Exactly. And last slide. So again, this is another drill and fill technique. This one is just done from the interior. And so, this has been traditionally limited to cellulose, but can now be done with fiberglass insulation as well. And it's an extremely cost-effective solution. So it's, just for example, this work scope, we ended up cutting a perimeter hole around the entire home along the exterior walls and removing existing fiberglass insulation. And so fiberglass insulation does nothing to impede the movement of air, and it can actually be seen. There's probably some great examples out there that you can see, but it acts as a filter, and so we were able to see where all that air movement was through the cladding and the fiberglass. And so before all these projects, this is probably one of those ones I'm most proud of, but, we blower door test before we go in, and we were completely unable to depressurize the home. And it was estimating probably about 12,000 CFM of leakage, which is extremely high. And so after the work scope, we brought the attic into conditioned space, conditioned the crawl space, and then re-insulated every wall cavity with cellulose insulation. And by doing so, we were able to drop the number to 4,000. So quite a big jump there.
Yeah, that's awesome. And so a couple of things just to kind of remember when we're talking about this or any other kind of drill and fill scenario is, again, ensuring that there are no bulk water issues in those wall systems. Just adding insulation to that is not going to help solve any sort of bulk water issue. And then I think the good thing about this, I'm sure there's a way to do this with the spray foam, but I think the good thing about this is, one, again, cellulose has very high thermal mass. It holds its temperature very well, good sound attenuation. It's a recycled product. Everything that's on the floor there at our installer's feet gets sucked right back up and put right back in the truck and reused on the next job. So, there's very little waste. It's all recycled material. They actually take down the pieces that they cut out of the wall system and they put them right back up, drywall mud them back up, and there's no need to go in with new drywall. So this is a very good way if you're able to get in and work in the house and you're not working around people's things. That could definitely still be an issue. And there's still a way to do it otherwise, but this will encase all of your infrastructure. This is a very good way to re-insulate a house, and that's kind of the reason we wanted to end on it. It really is the most success we've had in this kind of retrofit of wall insulation market. So I think Bill did a really excellent job on this house, and the homeowner was extremely happy on the back end, which I think was one of the most important things from where we're sitting. So I think that's all we had for you all today.